Thanks for coming. From the title, it might seem like this is a talk about performance, but I can assure you that there is nothing about performance in this talk. This is me. My name is Eirik, and I'm a JavaScript consultant and instructor. And I spend most of my time programming JavaScript, both on the server and on in the front end. Some people love to hate JavaScript. I just absolutely love it. Some things are rubbish, but the best parts are golden. And one thing that I like in particular is React. Not because React is React, but the idea behind React and what it enables. So there's other libraries with the same qualities as React, and even better ones more objectively, that are more pure. But the exact implementation isn't the important thing here, but rather what it enables. And to explain what I mean by that, So to explain what I mean by that, we can look at how you create a component in React. And in React, that's a matter of describing some UI based on some input. So the input here is some props, some data, and then the output is some UI. And it might become even more clear if you look at these functional stateless components, which are just functions, pure functions that take props and then return UI. If you want to see it without the JSX notation, you can see that it's just function calls, nested function calls. So we can use this component now to create a description, because the components here, they don't actually return UI. They just return descriptions of UI. So you could use this as a function that takes some input, and it'll give you a description of some UI. And that description might look something like this. For example, it's a plain object just describing some UI. So this is just a value. So the component doesn't actually render anything. It just describes the output. To do the actual rendering, you would have to use the React runtime. And it's the runtime that actually does the DOM manipulations and actually gets something to be rendered on the screen. So there's a runtime for rendering something to the browser. There's a runtime for rendering something to a string. And there's a lot of other targets as well, like native devices now. So the important thing here is that the runtime just takes a description of what to render, which is just a value. And then the runtime performs the actual operations to get something to be rendered on the screen. So what happens in React is that you might have some component tree which consists of these pure functions that just returns descriptions of what your app should look like. And then you have this rendering engine wrapped around your application. And then you might have the DOM on the outside. So that's completely on the outside. It's a bit of a misfortune that it's a bit far out on the outside. But that's not a part of our application. So what might happen here is that the React rendering runtime tells the component tree, could you please render yourself, and then pass me whatever description that yields. And then the actual runtime would patch the DOM to render this to the screen. And then maybe someone changes the state of your application. Then the runtime has to ask again, what is your output if the state is this? And then it passes back another description, and then it patches the DOM again. So what if we wanted to write a test case for our component now, for our application? we could just write a simple test case where we, for some description, we could produce some description here, and then we could just expect that to equal some description that we wanted it to yield. So this is just comparing values. We're not actually doing anything against the browser or any rendering here. We're just comparing descriptions. And since we have this new way of calling functions with JSX, this new syntax introduced with React, we can make it look even simpler, because if we use JSX, we could just expect that to give some kind of output producing this description, which would again just turn into an object, just a value. So what React did is that it made it easy to describe UI and to test your UI. And that makes me really happy, because that used to be really hard. If you think about like really imperative solutions like jQuery or other solutions where you don't have this divide between describing and the actual rendering. Another library I like really much is Redux. Not because Redux is Redux or the hype or anything, but I rather like the idea behind it, and especially Redux because it is the simplest implementation of this idea. You could pretty much create the core of Redux in 17 lines of code, maybe less. So if we take a look at Redux then, by the way, the logo here was really hard to draw for some reason. So if you look at Redux now, in Redux, you have this way of describing actions that might change the state of your application. And these descriptions are just values. So here it's represented by just a plain object. And then you have this so-called reducer function, which is just a mechanism that takes your previous state and a description of what to happen, and then it returns a new state based on that. So you are the one who decides how state is updated and how state is represented. And this, again, is used as input to create this Redux runtime, because the store is what actually handles all of your state. And then we can pass descriptions to this runtime by dispatching so-called actions. So the action here is just a description, just data, just a value, and then the runtime does the actual state updating. So if we wanted to write a test case for our state updating logic now, we could just define some kind of initial state that we wanted to start in, just define a set of actions that we wanted to process in our system. So we could say the increment action here has happened 3 times. And then we could just expect that the result of reducing all of those actions with the initial state and our reducer function, that it returns the state that we expect, so that we go from having the state 10 to having the state 13. So now again, Redux made this whole deal of describing state update logic a lot easier, and also testing your state update logic. And that again makes me really happy, because that used to be really hard, like a global mess. So what both React and Redux here have in common is that they've taken the fact that you're both describing and doing things, and they've separated it into separate parts. So one part is describing what to do, and the other part is actually doing things. And this is really great, because this means less complexity in the true sense of the word, because things are less braided together. You kind of have these separate boxes now to put the different things in. So that's really good. So now we have UI and state covered here. But the hardest thing might not be the UI and the state, but at least we have a third thing, maybe a fourth, which is how do I orchestrate all the asynchronous flow here in my application, because how do I decide when things should happen? How do I decide when to dispatch which actions when I'm doing things asynchronously? And if I'm having a lot of side effects in my application. But side effects, what is side effects really? So when I'm saying side effects here, it's everything that might interact with something on the outside, like the network, or printing something to the screen, writing something to a disk, maybe rendering something to some platform. Basically, anything that interacts with the real world is a side effect. And we need side effects because without side effects, our applications wouldn't actually do anything. They would just be pure programs that did calculations. And that doesn't really have any real value in the real world. And when we think about these side effects here in our, let's say, React and Redux applications, it usually comes down to the part where you're doing something asynchronously. Like, let's say you're getting some data from the server, and then you're going to populate that back. Maybe you're doing something else asynchronously at the same time. So if you look at this pattern here, which is called a thunk, you can see that we are dispatching actions at different times here. And the actual operation of dispatching something here or going to the network to get something is a side effect. So that means that if we wanted to test things here, we would have to write mocks, which is pretty unfortunate. But just to avoid coupling this to Redux and React, I want to make this example a bit more generic. So we could just say that we have a function, which we're calling a procedure here, which just does a lot of stuff. It gets a random number, it logs out that number. If that number is higher or lower than 0.5, it logs out something different. Then it does a request, and then it writes the result of that request to a file. So we have a lot of side effects here. So to visualize what happens here, we have this procedure, and then this procedure calls out to do a lot of side effects. So when we get a random number, you actually have to go to the computer and get some kind of entropy to get a random number. Maybe someone throws a dice, or in some case, we need to interact with the real world. And when you log something, you have to print something to standard out. If you make a request, you have to go to the network. If you write to the file, you have to access a disk, and so on. But if you look at this now, what you can notice is that there's no boundary here. There's no boundary between the thing that describes what to do and the thing that actually performs all of those things. So when we don't have those boundaries, we have to resort to things like mocks. So if we look at this procedure again now, you can see that if we wanted to write a test case for this procedure, we would have to mock out a lot of things here. We'd have to mock out math random, console log, the request thing we're using here, write to file, and so on and so on. And that makes me really sad, because who wants to write mocks? Who here enjoys to write mocks? No one, of course. And the worst thing is mocks that have a lot of behavior, because mocking behavior is the hardest thing, because to be able to test things, you have to mirror the behavior of the real thing, which can be really hard and expensive, and it has to be maintained alongside your actual application code. So again, what we want to do here is we want to take this and be able to separate whatever describes what to do from the part that actually does it. So it's time for a little story. A story about Frank Procedure, Johnny Runtime, and his evil twin brother. So this is Frank. Frank pretty much just lives in the world. where there's flowers, there's trees, there's the ground, and the sun, and all of that, things you're used to. And Frank can interact with the world. He can, for example, observe things. He can observe what time of day it is, what kind of temperature it is, and he can observe different events that happen in the world. And he can also interact with the world or mutate the world. He can do things like chop down a tree. He can dig a hole. He can pick some flowers, you name it. He can do a lot of things to manipulate the real world. But Frank also has some special characteristics, which is that Frank is incapable of lying. And he also has this very specific job. And he does exactly what he is instructed to, and nothing else. So that's Frank. So Frank's job is pretty much to, every day, his instructions are to wait for the sunrise. When the sun rises, you should measure the temperature. If the temperature is below 15 degrees, you should chop down a tree and make a fire because it's cold. If not, he should just pick some flowers and make a bouquet, have a nice day. And then, whenever that is done, he should wait for the next sunrise and do the same thing. So Frank is pretty happy because he knows what to do every day, and he does what he's supposed to, you might think. But can we really be sure that Frank is doing what he's supposed to for any condition of the world? It's been 20 degrees for the last 10 years, so we don't really know if Frank is going to chop down a tree and make a fire if it turns cold. But we want to make sure that he actually does that. So how can we make sure that Frank does exactly what he's supposed to for any state of the world? And Frank pretty much cannot answer what-if questions because he only does exactly what he's told. So we either have to wait for all of these different conditions to happen naturally in the world, which seems really inconvenient, or we can fake all of the conditions in the world. And that would include making a lot of plastic flowers and plastic trees and making something that could fake a sunrise. And that just seems really expensive and hard. Because the sunrise only happens once a day, so it would be really inconvenient just to be able to test things once a day. So faking all of these things in the real world is hard because that means that you have to mirror how the real world works. So what do we do then? First, we'll have to introduce Johnny Runtime. And Johnny Runtime performs tasks. If you tell him to do something, he'll do it. If you ask him, could you please tell me when the sun has risen? He'll tell you that. Could you tell me what the temperature is? And he'll tell you that. Could you chop down a tree for me? Yeah, he'll do that. But Johnny doesn't have any understanding of the order of things. He just He does single requests and then gives you a result back. So let's try another scenario here where we have both Frank and Johnny in our world. So it's the same world, flowers, but you can see now that at least some of you might see that it's supposed to be night. That's a night sky. But we'll have to make some restrictions for Frank here because we don't really want Frank to interact with the real world anymore. So we're going to have to build this wooden cabin around Frank with no windows. He has a door, but the only way he can communicate with the outside world is by passing notes under the door. He can't hear anything, can't see anything. It's nice and warm and cozy, but other than that, it's completely isolated. So let's see how this interaction now might go down. So we'll start out by, Frank knows that he's supposed to wait for the sunrise. So what Frank does is that he passes a note, a post-it note, under the door saying that, could you please, whoever is outside, notify me when the sun rises? And so the sun rises, and Johnny passes a note under the door to Frank to tell him that the sun has risen. Then Frank passes another note back and asks for, I want to know what the temperature is now. Like, he writes that on a note, could you please tell me what the temperature is? And Johnny, okay, sure, I'll measure the temperature. And then he passes a note back telling him that it's 20 degrees. And then Frank passes another note to him telling him to go pick some flowers and have a nice day. So Frank doesn't get to have any fun anymore, but Johnny does. So he picks some flowers, and then he passes another note under the door telling Frank that, yeah, I picked some flowers. I'm done. And then Frank passes another note telling him, could you please tell me when the sun rises? And then you have this loop going. So that seemed okay. Not for Frank, though, but like if you disregard humanity in this example. But how does this make it easier to test that Frank does what he's supposed to for all conditions? And that's where we have to introduce Johnny's evil twin brother, Bill Bogus McTesty. Bill Bogus McTesty, he will lie about anything. But the good thing is that he will take instructions about which lies to serve. And Bill actually never interacts with the world. He doesn't care about the world. He's really self-centered. This is his only job. He lies about things and takes instructions about what to lie about. So what if we replace Johnny now with Bill? So we start off the same. It's the night. It's the middle of the night. And Frank passes a note under the door telling whoever is outside to please let me know when the sun rises. And Bill gets the note, and he just passes the note back, telling him, yeah, the sun has risen. Like, it definitely hasn't, but he's just, yeah, why not? It's risen, sure. And then Frank passes another note back, telling him, could you please tell me the temperature? And Bill just, I don't want to measure the temperature. I'll just tell you that it's 0 degrees. So he passes a note back describing that it's 0 degrees. So Frank, doing his job, passes another note back out to Bill, because now Frank is supposed to tell whoever is outside to chop down a tree and make a fire. And Bill gets the note, he does nothing, and then he passes a note back in telling him that, yeah, I chopped down a tree and made a fire. And then that starts again, right? Now Frank asks for like the next sunrise. So the important thing to notice here now is that we can now test that Frank does the right thing for any state of the world. But we didn't really have to fake any behavior here. So we didn't make any mocks, we didn't make any plastic trees or any props. But rather we only mocked values, because the only thing that we had to mock here was what was written on the note passed under the door. And that doesn't have any behavior. That is just values. That is just data. So this seems like maybe this is a good idea to be able to test our asynchronous procedures. But how would you translate this into code? Like, how would you do something like this in JavaScript? Because obviously you cannot pass things in and out of functions in several places. A function takes input in the start, and then it returns something at the end. So clearly, using a function here just wouldn't suffice. So then we'll have to take a look at this really nice feature that came in ES6 called generators. Some other languages have had generators for a long time. How many of you have heard of generators? some of you, how many have actually used generators? Okay, not a lot of you. So then it's pretty fitting with a introduction then. So a generator looks very much like a function, except it has this star, and you have this new keyword called yield. So it looks pretty much like a function, but it doesn't act like a regular function, because if we call a generator function, it'll return something to you called an iterator. And if we use this new for of loop syntax that came in ES6 as well, in this case, it'll just by turn log out 1, 2, 3, because that was the values that was yielded out of this generator. And seemingly, it doesn't really care about this return statement, since it only logged out 1, 2, and 3. But we can also manually step through generators, or these iterators, rather. So we can create ourselves an iterator from this generator function, and then we can start stepping through this function. So an iterator has this interface where it has a method next that it uses to skip to the next point that is yielded inside the generator. So what happens here is that the first time we call next here, it skips down to the first yield, and then it returns an object with the value that was yielded, and it also tells you if this generator function is done running. And it obviously isn't done running yet, because we've just hit the first yield. If I call next again, it'll give me the value 2. It'll tell me that I'm still not done. I call next again, it'll skip to the value 3, and then I'm still not done. And when I call next again, it'll give me finished. So obviously now it does care about the return statement. So now I got finished out, and it also tells me that I'm done. Done is true. If I call next again, it just gives me undefined as a value, and tell me that I'm still done, like I don't have any more values for you. So let's take a bit more extended example here, where we have this generator function which will count to 3, like we have 3 yields inside here, but we'll also log out something here. We'll log in the result of yielding this value. So let's start out by creating this iterator instance, and then we'll call next. So what happens when I call next here is that the generator jumps down to the first yield, and then it gives me back the value 1 and done false. And the next time here, I'm going to call next with the value 5. And when I do that, it actually logs out first number 5. So it seems like we've been able to pass a value into the function here. And then it jumps to the next yield, and it gives me out the value 2 and says, I'm still not done. And then we pass in the value 10 on the next. It logs out second number 10, jumps to the next yield, and then it gives me back the value 3 and done false. And then I pass in the value 15, and then it logs out third number 15. And then it jumps to the return statement, and then it gives me the return statement value, and it says that it's done. It's done running. So what's happened here is that we've actually been able to replace those yield values there by putting these values into the generator function. So it seems like we're both able to get things out of generators and put things into them, which is pretty much what we want, because we want to be able to pass things between this boundary. And this might be exactly what we're looking for, because now we see that we can get values out, we can take values into the generator, and then we get this really good idea that why can't we just use this to pass descriptions of side effects out of the generator. Because now we have this semantic here to be able to pass just values in and out of these generators. So what if we create ourselves a function here? A function called call, which takes a function and then a set of arguments, and then it returns an object, which is a description of calling some function with some arguments. So to explain what I mean here is that if you use this call function, we could create a description of calling console log with hello and world as its arguments. That would give back an object here with that description. So this doesn't actually call console log with hello world, it just returns a description of calling it. So this actually doesn't do anything. To be able to do something with this, we would need some kind of mechanism that could take these descriptions and then perform these actual effects. So we'll create another function here called perform effect, which takes this description as input. And then this perform effect here now obviously only supports the call effect. And if it gets a call effect, it'll take the function, call it with the arguments, and then return a promise of the result. So in use, this would look like this. So if we made this description here of calling console log with hello world, we could perform that effect by just passing that effect to perform effect, and it'll log out hello world. Or we could just do this directly by passing an object describing this directly to perform effect. And that would just log out hello world. So again, what we've done here now is we've been able to separate the actual doing of something and then the describing. But there's still one thing missing here, because we don't really have who is going to make sure that this generator gets stepped through. Like, you don't want to do that manually. So we'll need some kind of runtime that would be responsible for actually running all of our procedures. So an example of a runtime like this would be a function that would take a generator function, which would then make an instance of that generator function, an iterator, and then we would recursively step through this, and whenever the generator yields some description of an effect out, we're supposed to resolve that effect, perform it, and then return the result back into the yield in the generator. So we're kind of just like, the generator is passing a description of doing something out and gets the actual value back. So this procedure now, where we're doing things directly, we're like doing side effects directly here, translating this over to a generator, we would replace all of the direct calls here with yields, which pretty much this creates a description of calling math random without any arguments. And that's what we push out of the generator. And then it's up to the runtime how to actually handle that. And you can see that all of the side effects here have been replaced with descriptions of side effects that we just push out of the generator. So if you look at this procedure now, it doesn't actually do anything anymore. It does nothing other than compute, because all of this is just descriptions. It doesn't actually log something. It doesn't write to the disk. It does nothing. It depends on the runtime to actually get anything done. So to run our procedure now, instead of just calling the procedure and letting it run, we're passing this procedure to our runtime. And this looks something like this, where we now have our procedure, like before, which is now a generator function, which yields descriptions of doing things out of it. So now we have a runtime like encapsulating our procedure. So the runtime starts stepping through the procedure. The procedure yields out some description of doing something. And then the runtime actually goes out and gets a random number and passes it back to the procedure. And then passes the data back into the procedure here. It steps to the next. It logs out something to standard out. That doesn't really return anything, so we're not expecting it to either. Then we're doing a request. The runtime goes out to the network, gets the result, and then passing it back into the procedure. And the same when we're writing something to the disk here. So the runtime is doing all the things here, and the procedure is just describing what to do. So what about testing this now? Because now we have a procedure that doesn't actually do anything. It just describes things, and then the runtime performs any of it. And between the boundary here between the procedure and the runtime, the only thing that passes that boundary is values, only data, nothing that has any behavior. So this is just plain values, plain data. So if you were to write a test case for this now, we could take our procedure, make an iterator out of it, and then we can start to step through it manually. So we can go to steps, like the first step here. And then we could expect that the first step here is that the generator yields out a call to math random. So we can expect that that's what it's doing. Then we can actually say that, OK, I'm going to fake this because I'm not actually going to make a random number. I'm going to tell the generator that your random number is 0.2. And then I can check that, OK, that means that the next step should be that he yields out a call to console log with the value 0.2, because he was supposed to log out the random number he got. And then this goes on, right? We can just observe what the generator yields out, and we can just pass fake data back to it. And then we can make sure that without ever doing a request here or logging or doing anything, we can make sure that the procedure does exactly what it's supposed to do for all different conditions, for all different values. So this, in the same way as React and Redux, makes describing asynchronous flow with a lot of side effects a lot easier, and also testing asynchronous flow, because we have found a way to separate the describing of what to do and actually doing it. And that, of course, makes me really happy. So this has just been an attempt to repurpose the underlying ideas behind React and Redux and all of these kind of functional principles here. Where what we're basically doing is that we're pushing all of the side effects all the way to the edge of our application, so that the core of our program doesn't actually do anything anymore. It just describes things. And then all the side effects are like way out on the edge of our application. And the most complete implementation of this idea is something called Redux Saga, which some of you might have heard about, which uses exactly this way of being able to declaratively describe side effects and uses the exact same semantics that we looked at. And this isn't just something that you can use in the front end, but rather something that you could use for anything that has a lot of side effects and a lot of complex asynchronous flow. Yeah, I'm not actually sure if I'm going to show the demo, but let's say that we had this program here. It's a program that is called slowprint, and what it does is that it sets up an infinite loop and says that the first thing that you should do is wait for there to come some data in on process standard in. Like if someone writes something into standard in, give me whatever they wrote. So now we have this new kind of effect here. Previously, we only had call, but now we also have an effect called take stream, which produces a description of waiting for a value on this stream. And when we've gotten some data there, we'll just make that into a string and then split that into an array. Because what we're going to do here is that we're going to like incrementally print out these characters with some delay between them. So we're saying here that while there's characters left in the array, put those into standard out, like print that back, wait for 50 milliseconds, and then go to the next one. So this is, of course, just a contrived example, but this is something that would be really hard to test without mocking out an implementation of streams. But now you could actually test this without using any streams at all, because you could just test that it does what it's supposed to do for different kinds of effects. So let's see if I can get this up here. Why? It doesn't let me move the window. Okay. It's going to be a bit hard to see, maybe. So we have this program now that when I write something here, if I write hello, it'll print it back to me with a 50 millisecond delay. If I write a lot of stuff here now, it'll just print it back to me, to the stream here. So the only thing I've used here is just a slight extension of the runtime and the code that we've been writing here now. So again, something that might be both hard to describe and hard to test might be made a lot easier by using this approach. And also, there's no callbacks here, and then there's no promises. It's just sequential code, which is also this really big advantage to using this approach, because it kind of abstracts away the whole deal of asynchronicity. So now we have these new effects here, like take stream, put something to the stream, and then we have an effect for making the process wait for 50 milliseconds. So you could pretty much make all of your own effects here, but Redux Saga has all of the useful ones already implemented. There's also a very similar construct called async await available now in JavaScript, which does pretty much the same thing for promises, where you can write code that looks synchronous but is in fact asynchronous. So why couldn't I just use async await here instead of generators? So the drawback with async await is that there's already a runtime for you there. You are not able to override that and step through your asynchronous functions. So you wouldn't be able to test it the same way. You would still have to write complex mocks. But for asynchronous code, just for going from like promises and callbacks, async await is very nice. So just an important note is that I'm not telling everyone to go ahead and do this thing, but if you're writing a lot of complex logic and you're finding yourself having trouble like getting to test this, you're having to write a lot of mocks, it's hard to see the actual sequential flow of your code, this is something that you should look at, and especially then Redux Saga. And that's my time. So that's what I have. If you have any questions, please feel free to ask now or afterwards.